Please welcome NVIDIA Senior Deep Learning Data Scientist, Katja Sirazitdinova, and Edge Impulse's Vice President of Engineering, Sergi Mansilla.
We're here with Katja. As they announced, I'm the VP of Engineering at Edge Impulse. I'm lucky enough to work with the amazing team that builds everything we're presenting here. But I think that we're already seeing a clear trend of a clear tech trend of tech that we're having here at Imagine today. We're seeing like how cloud AI is kind of converging with edge AI, and it's kind of becoming more and more indistinguishable. What kind of workloads can each do and cannot do? How can they be combined? We're seeing a lot of stuff like hybrid AI coming from Apple, Google. Like, what is your take on how can edge AI benefit from those big AI, cloud AI trends?
First of all, super excited to be here. Really nice. To your question, I see two major ways of connecting edge and cloud. The first one is, we know that it's not feasible to train at the edge. Training needs lots of data, lots of compute, big models, and to deploy these models, you can then take these models and optimize them and deploy them on the edge. And for that, you need this kind of like a bridge between like the data center and the deployment edge. It needs connectivity. We can also talk about continuous training where your devices are in operation and then you continuously collect new data and continuously improve your models. So this, for these approaches, hybrid is necessary. But we can also think of augmenting edge with server deployment when we talk about some large-scale, large models which are not fitting in the constrained edge devices. Because we all know that edge devices, they are constrained by many things. It's a form factor, so the chips are smaller, meaning like less tensor cores in NVIDIA devices. Smaller models. We also know that these devices are not constantly plugged into the power outlets, so we need to be also cautious about the data, and that's why it's also sometimes essential to offload the computations to the cloud, to server installations.
Yeah, so we're in the business of optimizing AI to fit in those super constrained devices, but a common question in the industry is like how soon we'll be able to, and we've seen some demos today, right? For example, on the ARM presentation, but how soon we'll be able to put stuff like LLMs on device, and also do we want to put LLMs on device? So one take is that LLMs are sometimes ambiguous on their output, right? And we're talking about industrial settings and places where you don't want any ambiguity. So how important is to have this kind of ability, LLMs, SLMs in devices, and is this something we want? Is edge AI inherently different than cloud AI? What's your take there?
What I observe in the industry are maybe two major trends in camps. One trend is taking these foundation models and trying to compress them and put them on the edge devices. The second one is to create smaller, specialized models which are experts in one and only thing but have no idea about anything else in the world. So I think those two approaches both are valid, and for different use cases you can think of one or another. And the pace of the technology is so fast, so tremendous that I won't be surprised then, like maybe very soon we'll be also able to put these large language models effortlessly on the smallest chips possible. The chips improve, the models get smaller, and there are plenty of optimization techniques, like we can talk about distillation, quantization. So before we knew that, we had like floating point 32. Then somebody said, yeah, what if we just round up until floating point 16? And then it worked as well. But then somebody clever said, what if we map actually the floating point range to integer range, and then quantization was invented. And now we are looking at integer 4, or some companies are looking at binary quantization, and I think the possibilities are really limitless here. Then model pruning, where we get rid of the neurons in the networks which are not participating in the final output, what the model is providing. Then when talking about transformer architectures, there are different ways, like, you know, that attention mechanism, it has this like key value pairs, and it generates these key value pairs for every token in the sentence with a relationship to other tokens. So we can actually optimize that by caching these key values. And there are also multiple techniques where you can optimize this caching, and it helps further to improve performance of these large language models. And there are many other techniques which research community is working on.
Yeah, I think that one of the most popular videos this year was our CTO, Jan, demoing how to use generative AI in pre-processing data that we later use on our models, right? So I think that had good reception because it's an original way to enhance data, tag data that perhaps is not good enough, and that is a distillation, if you will, that makes the model more precise, more efficient, and so on. So it's a way of it's a different kind of hybrid in which you use big AI to pre-process data that you later use to train the model. And I think that's for now it's been very successful.
That's a very great point, actually. Like you can convert any kind of data into embeddings and tokens. And you can also use these models to convert, let's say, images. Like when we're talking about vision AI, you can convert images in the embeddings, and also like moving embeddings from device to device and working directly with embeddings optimizes things.
So just this morning, we had when we were setting up our demos, you may have seen some conveyor belts there in the main room. On one of the conveyor belts, we trained models on different conveyor belts than the ones they sent over here, right? So we were expecting some different in model precision, but reality was like, it was drastically different. So we were like freaking out a bit, like, oh, we're gonna have time to train the model, is this gonna work out? Of course, our engineers, Josh and David, were on it, and they made it work, and they retrained in record time and all. But I think the point stands, at some point we were looking at the data that we were using, because we were time constrained. We were trying to train the model with a limited set of data, and it was not enough. And then we managed. But that's a big deal in our industry. Like how much, and it's a question that keeps coming from different customers and in different shapes. Like how much data do I need for a model to be enough? How much synthetic data should I use? How can it all be synthetic data? Because maybe I don't have good data, or maybe my data is not well labeled, or has no labeling at all. So I think that I'm interested from NVIDIA's point of view. Like, is there anything that we're expecting? Which right now the mantra is like the more data, the better labeled data you have, the better the model. I just think it's pretty reasonable. But is there anything coming that for our customers, for example, that they wanted that much data, or they can use synthetic data just to train their models?
I think the technology is already here, and today I've heard many times Omniverse, our platform, mentioned, and that also made me really happy to see the platform being put in really good use. So Omniverse is our platform for collaboration and also like a database of virtual assets to create virtual worlds, and it comes with many different applications. So you can think of it as a platform for simulating and building digital twins, building 3D worlds, but you can also create synthetic data. So once you have the digital twin of the warehouse, let's say, of an object, So what do we actually understand by digital twin? It's a representation of an object or subject or the whole concept in the virtual world. So it's a fake data. And with this object in the 3D world, you can then generate different views of this object. You can randomize appearances of this object. We call it domain randomization, where we can randomize textures, we can randomize shapes. And with all this domain randomization, we can ensure that the models we train with the data are getting as robust as possible. Sometimes I saw my colleagues who were working a lot on this topic, and well, I had also experience working in this. You can create really funky objects, like a cat with pink fur, and we would then think like, yeah, does it make sense? So it turns out that if you create a bigger range of examples than the reality encapsulates, then you make sure that you're actually solving the reality problems in this, this whole range of solutions. So synthetic data is great. And I was very skeptical when I was just starting working with synthetic data. And I basically put myself into this challenge. Can I train a model on purely synthetic data without using any real data? I was very skeptical, but apparently it worked really well. So we were partnering with one of our customers, and a big industrial company, and they were developing a solution for PCB defect inspection. And they had a small data set, like 30 images, and I partnered with an NVIDIA designer who was like very skilled in Omniverse and creating synthetic data. And we basically reproduced the data set they had, but like was introducing different defects there. The first model I trained with that was horrible, didn't work at all. But we then took another look, and it gave us the perspective, like what could be improved there. So it took us 3 iterations to train a perfect model with like 99% of accuracy, and 99% of accuracy on real data. So the customer then collected more real data, more real samples. And that got me really convinced that with 0 real data, you can actually train a model which would perform perfectly on real data.
That's crazy. I still remember when synthetic data was there, but it was just a crutch.
Yeah.
You always needed real data, and you could kind of fill the gaps, and it was not advisable to use synthetic data.
You still need the real data for testing. I believe that it's essential to test on real data.
Yeah, that was my next question. It was overfitting and other problems. Just moving on a little bit, what's NVIDIA's take on the edge? We see, obviously, we work with NVIDIA. There's the Jetson Nano, but NVIDIA is pretty much a cloud AI, big AI company, and at least that's how it's perceived out there. What do we know of their edge strategy? How do you feel
it's a very common misconception, and actually, yeah, it's already a big improvement because many know us as a semiconductor company. When I was starting at NVIDIA, before the whole AI hype, many people also saw us as a gaming company, but actually we position ourselves as a platform company, accelerated computing platform company. And the essential goal is to solve all kinds of computing challenges, be it in the cloud, on the edge, and edge is an important part also of our platform and the ecosystem. So we develop hardware, but we also develop lots of software because platform wouldn't be possible without the end-to-end approach. We develop our hardware devices like Jetsons. You may have heard about Jetson Orient devices, our powerful edge devices. We also develop software which runs on embedded devices, and we develop software which helps to optimize the models for running on these edge devices. Embedded and edge AI is everywhere, like autonomous driving, robots, drones. So these are crucial applications in the industry, and we cannot neglect them.
Do you think it will converge anytime soon? Like as we said at the beginning, like there's the 2 tiers of AI, like the cloud and edge device. We need the real time, we need the decision. how soon until, and NVIDIA makes some very powerful devices, like how soon this separation will not matter, you think, from your point of view?
I think the development is natural, so we see trends in hardware getting smaller and more powerful and needing less like power energy, but also the models getting more efficient, and at some point this will converge. But also at the moment now, we don't have to solve everything through like one-fits-all solution, and we can design solutions on a use case basis. So sometimes we don't need huge models running here at the edge, right?
So you travel around the world talking to customers, advising them. Each customer is a different story, different world. What would you think, what do you hear the most from customers? What are their main problems that you hear, and how do you advise to solve them?
So the first big problem I usually see is accuracy. Well, how to train a model which is accurate enough, which is generalizing well on their data. And that comes inherently from the lack of data. So getting good quality data is the biggest challenge. Then once you have developed like a model, well, let's say once you have collected good data or created a good synthetic data set, the next challenge would be take this model and make it run within reasonable latency and also within reasonable throughput on the devices, be it a data center or edge device. Latency is a big problem all across the fields, not only on the edge, and especially on the edge where we have the small chips which have limited compute. Then once you have solved this problem, let's say you've optimized it all, the next problem would be how do you deploy it at scale? So let's say you have the fleet of devices all across the world. So how do you update your models? How do you maintain your devices? These are the three major challenges like the whole industry is solving. And it doesn't matter if it's edge AI or data centers. They're universal challenges.
That's right. How much do you think, so one thing I observe with our customers is that this industry is changing so fast, is evolving so fast, both the hardware embedded industry and the AI ML industry, that one of the main problems we find is that nobody knows what's possible. Nobody knows what they don't know. It's hard to, and when you talk to customers, I think there's often a very big task of educating, studying their use case. Like people sometimes default directly to the big devices like the Jetson when they could be using MCUs. And there's a lot of hype and confusion about what can be done. How much do you find, how much do you encounter this in your day-to-day when you talk? Because probably you're at NVIDIA, you're with researchers, and then you get out in the real world and you say like, oh, the world is still trying to make sense of everything that's happening, right? And how much do you think that's a problem for the industry to evolve at this point?
Yeah, we are talking to customers at different stages of development. Some of them just have heard that generative AI exists and they want to use it, but they don't know how. So in these cases, we come and talk to them and see what's possible with the data, with their workflows, with their processes. Some customers, they already have defined problems, so they say, okay, we have this problem, we know that generative AI can help us, but we don't know how. And then there are also customers who are on their own and they are already developing solutions, but they need like a little help in like making the final push in optimizing these solutions, in deploying at scale, so different levels. What we also observe is that we're at this exciting time when like we are already at this stage when we can deploy generative AI. Because like 2 years ago, what we've experienced is like the big bang of generative AI when the whole world has changed and people discovered that, but everybody was just excited and not knowing how to start with that. The last year was the year of exploration when like the industry started seeing, okay, what we can do with this technology. and this year we are already seeing like it's being put in production. So it's very exciting and really exciting to see what's coming next.
What are you working on these days?
Working on different tasks. So I'm a solutions engineer working with customers directly, and my day-to-day job is supporting customers in their journeys. And we have different use cases. Like some of my customers, they develop the holistic workflows with agents and large language models. And it includes like data pre-processing, then training the models, pre-training the models. RAG is another big thing, and many of my customers are utilizing RAG. So by RAG, we understand the augmenting your large language model with some vector database, where you put factual knowledge in this database, and then when you're using your model in production, you can actually rely on the factual information, pulling it from this RAG system. And I said vector database, meaning that you transform your data into the embedding form, and you store it in the form of vectors in this database, which makes it more efficient to query the data. You no longer need to rely on complex SQL queries, but you communicate with the system in a natural language. So this is really amazing. And it can work for text, but it can also be multimodal. So as I mentioned before, you can also convert images into embeddings, and then you can talk to your RAG about anything.
It's interesting because it makes me think that in the embedded context, if you manage to have RAG working on, you can augment the model with the data that the device is gathering in real time, right? So this data is augmenting the internal database, and the model can use that and kind of improve itself depending on the conditions and the sensor data that is coming in, and doesn't need any external influence or network or anything.
Also RAG eliminates the need for excessive fine-tuning, meaning that once you have your model, which is capable enough of understanding human language, you don't need to retrain it very often, because the factual information can be stored in the database, and then you use the model as a medium to communicate to your database, but then you don't need to store the information in the model itself. I think it's a big breakthrough, actually. It's from last year, and it's very promising also for edge devices.
Yeah, because the model then is smaller by nature.
Exactly.
And what is the disadvantage? Like this all sounds amazing. What is the problem? Is it as good as a model trained from the get-go?
So different challenges. Like the biggest challenge I see now is working with like very structured data, like PDF documents, where you still need like the semantic relationship between the tables and diagrams on your PDF document and the text referring to these diagrams. I see many teams working on that. We at NVIDIA also have some solutions for that, but it's still a very challenging task.
What about distillation? What role does it play? Can it be combined with RAG? How do you see these different techniques for reducing models?
I mean, I wouldn't necessarily connect it with RAG, because, well, RAG is just a concept which you can use with any kind of model, distilled model or large language model. But distillation is an important concept. So with distillation, you can take a huge model and you can distill it to some specific task, and you can make it smaller. And it's then crucial also for edge devices, so it makes this model fitting in the edge device.
How do you decide when doing distillation? How do you tune it? What's that iteration? How does it look? Like how do you decide the model is good enough? Is it testing with real-world data? Like how would you go about in the process? You as a scientist, like, okay, this doesn't fit in the device. I want to make it fit, but not too simple that it's not good anymore. What would be your process?
So, first of all, actually not many people are doing distillation, although like the concept is really promising. I don't see this happening much in the industry. There are multiple ways of doing this. The most popular is the so-called teacher-student approach, where you have one big model and then one small model of the small architecture. and you're teaching the small model with the information from the big model. So you're given a task, and then you optimize the small model weights based on the tasks you give to the big model. Really interesting concept, but yeah, as I said, not many people in this industry are doing that.
Interesting. So, what is going back to NVIDIA, the brand? What do you think is next? You mentioned like for the last 3 years, what was the big trend? Mm-hmm. Like what's coming? Clearly, NVIDIA is leading the industry in many ways in AI. So probably you're the most well positioned to say like, what do you think is coming? What's the next big thing? Mm-hmm. What advantage does NVIDIA have there, given their position and their resources, or is it free for all in which we're still in a position with a new company with new ideas, algorithms could make a big impact?
So I would say that we are living in this very happy years when AI is getting democratized. And the big trend in the industry, and we at NVIDIA, we are trying to support it as much as we can, is that companies will stop pre-training these foundation models because there's so much already available which can be reused. And instead of pre-training them from scratch, the industries will be using these models, and they will be fine-tuning these models for the domain-specific areas. So instead of going out there, building a large transformer and collecting millions of data samples, you would focus on your specific domain area, and this will make AI accessible for everyone. So here at NVIDIA, we have introduced the technology. If you attended the last GTC here in San Jose, you saw Jensen announcing NIMs, the so-called NVIDIA Inference Microservices. So microservices is another big trend. What do we do in these NIMs is that we take state-of-the-art foundation models trained either by NVIDIA or by our industry partners, big companies like Google, Anthropic, Mixtral. And we take these models, our engineers optimize these models, we deploy these models in our Triton inference server, and then we wrap it all in a container, and we offer it with an API on top. So these NIMs, these containers, they become building blocks, which you can then use in the so-called AI workflows. You may have heard also about AI agentic workflows, which is another big trend these days, where instead of, designing like the heuristic application, you actually have a number of large language models communicating to each other, and this is really amazing. So we are trying to offer the so-called blueprints, which actually contain the whole holistic approach for solving one or another problem. So let me give you an example. You can have a talking kiosk, right? So in the talking kiosk, you design an avatar using our Omniverse platform. So it's, let's say, a person or a character. And then you have another model connected to this avatar, which would then process speech. It will have ASR, automatic speech recognition, available. It gets converted to the text. The text then is processed by a large language model, which understands what you are asking the model. It goes to the RAG system, and the RAG gives you the factually supported answer, which you then convert also in a human language, and then serve it to your user with text-to-speech capabilities. Wow. So this is the whole workflow, and we already have a blueprint for that available. Another great example could be you have a digital twin of a factory, let's say, and then you simulate robots running in this factory, which is actually connected to the real-world robots running embedded edge devices. And then you can optimize their routes through the factory or warehouse. And we have the technology called co-opt for that, for like graph optimization. These are the blueprints and the connected workflows, and this is the future. So the blueprints and the end-to-end holistic workflows is a big trend these days.
And you mentioned that it was also Anthropic and Mistral, and these people are. So is it kind of a standard in the industry? Are we at the moment in which the industry is getting to a point in which we generate standards because everybody's doing their own thing, right? And it's depends on the companies. Is then their interests are not to have a standard, but I think the industry is maturing enough that these standards would be interesting for users, APIs, and all. And NVIDIA plays a big role in that.
Yeah, so I think the reason here is that to create a foundation model is very expensive. So you need a huge data center running for like weeks and months to train this model, and it's a huge effort. So of course, not everyone in the industry can afford that. And those players who specialize on that, they're working hard and they're investing a lot in creating these models. So these models are then being used as the state-of-the-art, and they can be further adopted by industries.
Got it. I think we're literally at a time. It says 0 seconds. So thank you, Katja, for your insights. And if you guys want to continue this conversation outside, we'll both be available, and we can keep talking about NVIDIA, the edge, and everything else. Thank you very much.
Thank you, Sergi. Great chatting.